Hello everyone, welcome to this part. I'm Yilong Yang from the University of Macau. In this part, we present a ServeNet, a deep neural network for web service classifications. This is the content of our paper. Let's move into the motivation part. As we know, automatic service classifications plays a crucial role in the service discovery, selection, and composition. There are several works using convolutional machine learning methods to automatically predict the classification of the services. However, when we're predicting web services that contains multi-labels and more categories of each label, only less than 50% accuracy can be achieved. Those work are highly rely on the quality of the feature engineering, which are normally both difficult and expensive for the service classifications in the practice. Deep learning is a promising alternative which can automatically abstract the lower-level representations from the raw data to high-level features without feature engineering. And the deep learning achieves best performance in both image and text classification problems. Based on that, we present a novel deep neural network ServeNet that can automatically abstract features from both service description and service name, and then automatically merge them into a unified features without feature engineering. And also, ServeNet solves the content-independent issues and the limitations of the service description, which provided in the IEEE 19 by introducing the dynamic embedding on mini batch set. And ServeNet achieves a higher accuracy than other machine learning methods for service classifications on 50 category benchmark. Okay, let's see the related work. The original ServeNet is present as a working in progress papers. That is the stacked deep learning neural network. Compared with other stacked and deep neural network, such as the recurrent CNN and the LSTM, ServeNet adopts 2D CNN with a bidirectional LSTM. 2D CNN can not only extract the local features between adjacent words, but also the small region of the feature inside of a word. That is a word stem than the 1D CNN. Bidirectional LSTM, which can extract the global sequential features from both past and futures, that makes deep learning neural network achieve the better performance with the text information. The related deep learning methods and ServeNet in IEEE 19 have several problems. They only use the service descriptions to classification the web services. That means they do not use any other information in the service specifications for this classification task. They're using content-independent embeddings to encoding the web services that make each word of the service description embedded as a fixed vectors without considering the position in the sentences. They also use a fixed length zero paddings to pad all the description of the services to the same length. That will lead the dataset sparse when the dataset contains a few long sentences. The new proposed ServeNet solves those above problems. It can not only abstract features from the service descriptions, but also the feature from the service name, and then automatically merge them into unified features. It adopts a bidirectional encoding representations from the transformers for the dynamic context-dependent word embeddings on both service name and the service description. And also, it adopts a mini batch padding to pad service description name to the same length when the services are in one mini batch set. Okay, let's see the ServeNet architectures. The ServeNet takes service description and service name as input and output the service classification. it can contain 4 parts. First, the service description embedding and a feature extraction. Second, service name embedding and its feature extraction. Third is the feature merging from both of two features. Finally is the task layers. You can see ServeNet takes the service description and service name as input and output the service categories. For the service description, we first using BERT, embedding the description, and then using 2 CNN and 1 bidirectional LSTM to feature extraction. For the server name, we're only using the BERT for embedding and feature extraction. After extract those features, this feature is merged into a unified features, and then the task layer can predict the service class categories based on the unified feature. This is a hyperparameter of about the network, and this is the hyperparameter of the training. Okay, let's see the evaluations. First, we talk about the dataset preparation. Okay, first we jump into the service collections. The service is collected from the web program API share platform and store them into the JSON format named as WS dataset. After basic cleaning up and clean up the empty services, the dataset contains 15,340 services with 401 categories. Each service has 20 descriptors. In this paper, we only take 3 service descriptors: titles as the service name, description as the service description, and the primary category as the service classifications. After the basic service categories analysis, we found only 41 categories contain the number of the services greater than 100, and more than half of categories contain the number of the services less than 10. By eliminating the one-shot small set category and keep the big set category to make the dataset more balanced, the service dataset contains 10,943 services with 50 categories. Okay, it's time to split the dataset to training and testing set. Our dataset, as a basic analysis, we can tell that the dataset is imbalanced. So the random selection, it cannot make the training set and test set conform the same distributions on the small size categories. So we revise the random selections by keeping the same proportion of the training and test set on each categories. That will make the test set and training set conform the same distributions. Finally, the training set contains 8,733 services and test set including 2,210 services. As we know, in the original ServeNet, they have the limitation about the description length. So in these papers, to get rid of these limitations, we're using dynamic padding to each mini batch set, so that can accept the arbitrary length of the input. We first sort services in terms of the length of the service description, and then embedding the services in each mini batch set to the same length. After this processing, the new proposed ServeNet can accept arbitrary length input without losing the training efficiency. In the practice, the easier way to accept the arbitrary length of the input is to set the batch set to 1, but that is not efficiency. The training unit of the neural network is based on a batch set, So we only need to pad in the services to the same in the each batch set. That can make this balance. Okay, let's say the evaluation matrix. Top 5 evaluation matrix is usually used for the multi-classifications problems. When the multi-classifications greater than 10. What is the top 5 prediction? Top 5 prediction is correct when the top 5 prediction labels contain the target category. So the top 5 accuracy on the special category is the number of the total number of the top 5 correctness number divided into the number of the services in that category. What is the top 5 accuracy on the whole dataset? That is the average of the accuracy on all categories. Okay, let's see the experiments. In this paper, we compared 10 machine learning methods from the conventional machine learning methods to the deep learning models for service classifications on the proposed server dataset, which include naive-Bayes, random forest, SVM, AWS CNN, recurrent CNN, LSTM, Bell LSTM, CLSTM, as well as the original ServeNet in AWS 19. All the models are trained and tested on our servers and the Google Colab. Okay, the good news is all the source code and the dataset are available on our GitHub. You can use that link to read them. Okay, this is the top 5 accuracy and top 1 accuracy on the test set. You can see that the new proposed ServeNet can achieve the highest accuracy in both top 5 and top 1 accuracies. And also you can see the deep learning models have a higher accuracy than the conventional model. And also to comparison with the original ServeNet, we have a big improvement. For the top 5 accuracy, it approximately 3% improved. For the top 1 accuracy, they have the 6% improved. This is the accuracy on whole dataset. How about the accuracy on each category? Okay, we're using the radar figures to see how this top 5 accuracy look like. We put all the results about the accuracy on all the models. We can see the right line is the ServeNet we proposed. It have the biggest area, and also after counting the standard deviation about the category, each category of all the model, we found the ServeNet have lowest standard deviations, and also if we count the number of the highest accuracy on each category, the ServeNet have the most highest values. So let's see some limitations. ServeNet has the highest accuracy and low variance in service classification problems, but it still does not work well on some of the categories. When the categories have a limited number of the data points. And after analysis, we found the failure predictions are mainly from the fact that the service name and description does not contain the information about the target category, but contain the information in other category. So we should invent more advanced models to enable networks to discover those conflicts. And also we can collect more high quality data in the practice to fix this problem. Okay, and let's see the conclusion. In this paper, we introduce a novel deep neural network ServeNet for the service classifications. It can automatically extract features from the service name and description, and then automatically merge them into the unified features, and finally predict the service classifications. It trained and tested on the service dataset with 10,943 services, including 50 categories, and achieved top 5 accuracy 91.58% and top 1 accuracy and 69.95% respectively. The benchmark demonstrates that ServeNet is robust, that can achieve the best performance than other machine learning methods. For the future, we can do more work. For example, we can make an explainable ServeNet. And we can also do some transfer learnings from other similar problems, just like the app classification problems. We can also extend the 50 category to the 400 category, because in all the dataset, it's including 400 categories. And also we can do some collaboration with our previous work about the requirements modeling and prototype generation to generate the web service directly from the requirement model. That work is presented in IEEE 19 and the RE 19. Okay, this two QR code is, first one is my website, and second is the I'm2PT website. Thank you.